Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most beautiful and unsettling questions ever asked. How could everything, the stars, the galaxies, even us, have come from nothing at all? We'll trace the story of how humanity learned to measure the universe, and then how that same search led us to discover that the emptiness between things isn't really empty at all. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly enjoy these calm explorations of wonder. And when you're ready, leave a comment to tell me where in the world you're listening from and what time it is for you right now. It's always a joy to see our small constellation of listeners scattered across the planet, each in your own moment of night. Now, feel free to dim the lights. Maybe let the hum of the room become your background music, and let's gently begin our story together. Imagine holding a single grain of sand between your fingertips. It's small enough that you could lose it if you breathe too hard. Now imagine that grain as the sun, a tiny glowing speck among hundreds of billions of others. Around it orbits a handful of planets, one of which carries you. That planet spins silently through a sea of dark, and yet that sea is anything but small. Our sun, that one grain of sand, sits inside a galaxy called the Milky Way, a spiral of 200 billion other suns. And the Milky Way itself is just one of about 100 billion galaxies scattered through the observable universe. The number of stars out there is greater than all the grains of sand on every beach on Earth. When you think about that, it's hard not to feel a strange mixture of awe and calm, a reminder that the chaos of life is part of a vast and balanced stillness. What's remarkable isn't just the scale of it all, but that from our tiny vantage point, living on a barely visible speck, we've managed to deduce so much about what the universe looks like. The night sky might feel like an infinite mystery, but it's also a kind of mirror. When you look up, you're seeing the record of everything that has ever shone, written in light that's still crossing space to reach you. It's easy to imagine that the people of long ago lying under the same sky must have felt the same mixture of wonder and confusion. Thousands of years before telescopes or theories, the night seemed to speak a simple truth. The stars must be fixed to some great shell that surrounded the Earth. The universe, they thought, was a perfect dome, a celestial ceiling turning slowly overhead. For centuries this vision felt right. The stars didn't seem to move relative to one another, and the heavens appeared eternal. But every so often, something happens that breaks the illusion of permanence. In the year 1572, a new light appeared in the night sky. It was brighter than Venus, so bright it could be seen during the day. People called it the phenomenon, and many thought it was a divine sign. Priests preached that it might be the same star that had once guided the wise men to Bethlehem. But one man, an English astronomer named Thomas Diggers, saw it differently. He realised that this new star wasn't nearby. It wasn't in the sky's dome at all. It was a distant sun that had exploded. That single event cracked open the old universe. Diggers began to wonder, if one star could appear and vanish, then maybe the stars weren't painted on a fixed shell. Maybe they were scattered through an endless space. He published his idea a few years later, hiding it almost casually inside a translation of Copernicus. On one side of the page was the familiar model of the cosmos, with the sun at the centre and a neat boundary of stars surrounding it. On the other, Diggers erased the boundary completely. The stars, he said, continued without limit, upward and outward forever. It was the first time a European scientist had seriously imagined an infinite universe. The thought was both liberating and terrifying. Suddenly, the cosmos had no walls, no edge, no centre. Humanity was not in a grand enclosed system. It was adrift in boundless space. This new idea also raised a haunting question that would puzzle thinkers for centuries. If the universe really were infinite, filled with an infinite number of stars, then why was the night sky dark? Every line of sight, in theory, should end at a star. The sky should blaze with light, not silence. That riddle became known as Olbers's paradox, though Thomas Diggers was the first to notice it. The answer wouldn't arrive for hundreds of years. It would take the discoveries of Einstein, Hubble, and modern cosmology to explain that the universe hasn't existed forever, that light itself has only had a limited time to travel. But back in the 16th century, it was just a mystery, and a strangely comforting one. The darkness of the night sky hinted that the cosmos might be larger than human imagination could hold. You might picture Diggers standing under that same darkness, watching the new star fade until only memory remained. The silence around him wasn't empty, it was possibility. For the first time, the human mind had begun to step beyond the shell of the heavens. As the centuries drifted on, others would follow that same path of curiosity. They would build new instruments, polish mirrors until they could see infinity, and measure distances so vast that numbers would lose meaning. From these efforts, the first faint map of everything would begin to take shape. And as we drift further into the story, the light of those early stars will guide us toward a quiet workshop, where a brother and sister spent their nights shaping molten metal into windows, through which the universe could finally be seen. The night sky has always been a comfort, a pattern of light so steady that ancient people thought it could never change. For thousands of years, humanity looked up and saw perfection, a great crystal sphere turning above a still earth, each star a pinhole of divine light in a flawless dome. The heavens, they believed, were the one part of creation untouched by change or decay. Everything below the sky grew and perished, but the stars were eternal. And then, one night in the year 1572, that perfect sky betrayed them. It began quietly, as the best stories of transformation do. A few people in northern Europe noticed a new point of light near the constellation Cassiopeia. It wasn't faint, like the dim smudges of ordinary stars. It blazed brighter than Venus, visible even in daylight. Some said it was a sign from God. Some feared it was an omen. For most, it was a shock, a flaw in the most flawless thing they knew. That winter, a young Englishman named Thomas Diggers stood under the cold air and stared at the newcomer. He had been raised on the teachings of Aristotle and the harmony of spheres, yet the sight before him refused to fit. This new star, what we now call a supernova, seemed to have appeared out of nothing. And if something new could bloom among the supposedly eternal stars, then perhaps the heavens were not fixed at all. Diggers watched as the light slowly faded over the months, its brilliance softening back into ordinary darkness. But the question it left behind glowed even brighter. If the stars could change, could they also move? Could the sky be deeper than anyone had imagined? Diggers was part of a small circle of thinkers fascinated by the work of a Polish mathematician named Nicholas Copernicus. Copernicus had proposed, half a century earlier, that the sun, not the earth, was the centre of the cosmos. It was a radical idea, but still a bounded one. In Copernicus's model, the planets orbited the sun inside a closed bubble of stars, the outermost shell of creation. Beyond that, nothing. But as Diggers pondered the dying glow of the supernova, he began to doubt the existence of that shell. Perhaps, he thought, the stars were not stuck to the edge of a sphere. Perhaps they stretched outward endlessly. In 1576, he published his own translation of Copernicus's book, but quietly added something extraordinary. Beside Copernicus's famous diagram showing the sun at the centre with the planets in neat rings, Diggers redrew the stars. He erased the boundary that held them and scattered them freely into infinite space. It was a small act, just ink and paper, but it changed the way we imagine reality. That single sketch was the first time anyone had pictured the universe as infinite. There was no outer wall, no fixed border between heaven and nothingness. The earth was not the centre, not even the middle. We were adrift in endless dark, surrounded by suns, without number. At first, the idea was almost too vast to grasp. An infinite universe? How could the mind hold something with no edge? Some found comfort in it. The heavens now seemed grander, closer to the idea of eternity. Others found it terrifying. If the stars went on forever, where was God? Where was meaning? Diggers himself saw beauty in the boundlessness. He wrote that the stars might be infinite in multitude, scattered through infinite space to glorify an infinite creator. But infinity brings its own puzzles. One of them, simple and haunting, would echo through centuries of thought. If the universe truly stretches forever, and if every direction contains endless stars, then why is the night sky dark? Every line of sight, in theory, should end on the surface of a star. The entire sky should blaze with light as bright as the sun, yet it does not. The heavens, for all their brilliance, are mostly black. This riddle would become known as Olbers' paradox, though Diggers was the first to ask it. For generations, no one could give a satisfying answer. Maybe dust blocked the starlight. Maybe our eyes were too weak. It would take 4 centuries, and the discovery of the expanding universe, for scientists to understand that the darkness is not absence, but time itself. Light from the farthest stars hasn't yet reached us. The sky is dark because the story of the cosmos is still being written. Still, for Diggers, none of this was yet known. All he had was an image, a sense that space went on without end, and that the stars were suns scattered through an infinite sea. From that image would grow a revolution. Once the universe could be infinite, everything else would have to change. For the first time, humanity was no longer enclosed. We were floating. The ancient dome had cracked open like an eggshell, and through its fracture spilled the idea that space might be alive, endless, mysterious, and still unfolding. You can almost picture Thomas Diggers stepping back from his drawing table, the ink on his diagram still drying. Outside his window, the winter sky is calm again. The bright intruder has vanished. But he knows now that the heavens are not fixed, and that even the smallest flicker of light can rewrite the structure of everything. There is a quiet poetry in the way the universe teaches us, not through thunder, but through change. One star's death becomes another mind's birth of an idea. The cosmos reveals itself not in noise, but in subtle rearrangements of light. As centuries pass, others will follow the path that Diggers opened. They will build instruments far beyond his imagination, trying to trace the contours of the infinite he glimpsed. From his single diagram will come telescopes, observatories, and theories of time and space. And yet, no matter how complex our models become, they will always return to the same childlike wonder that first broke the shell of heaven. A question whispered into the dark. How far does it go? From here, our story begins to widen. The light from that supernova will fade, but the curiosity it awakened will not. New eyes will turn upward, guided by craftsmanship instead of parchment, by molten mirrors instead of ink. The trail of discovery leads us gently toward a small, firelit workshop in England, where 2 musicians will turn their hands from sound to starlight and make the infinite visible. A quiet exploration now carries us from Thomas Diggers's ink-stained parchment to a small candle-lit workshop more than 2 centuries later. The age of infinite skies has arrived, but the instruments to explore them barely exist. In a modest home in Bath, England, the smell of molten metal drifts through the air. It is the smell of patience, of human hands trying to give shape to wonder. Inside, 2 siblings are at work, William and Caroline Herschel. By day they make music, violins, organs and choirs filling the air with sound. By night they turn that same sense of harmony toward the stars. William, tall and serious, was once a military musician. He has a habit of talking in rhythm, of measuring thought like melody. His sister Caroline, small and sharp-eyed, keeps time beside him, her notes filling pages as steady as a metronome. Together they melt and pour a shining alloy of copper and tin into heavy moulds. As it cools, the surface gleams faintly, catching candlelight like a pool of quicksilver. Then begins the long, aching process of polishing. Hours, sometimes days, grinding away tiny imperfections until the mirror becomes a flawless liquid eye. It is hard work. The air grows thick with smoke and metal dust. The floors bear dark burns where molten drops have spilled. Some nights, the mirrors crack, and the work begins again. Still, the Herschels persist. They are chasing not fame or wealth, but clarity, the kind that comes when an idea becomes visible. William's telescopes are unlike any that came before. Instead of glass lenses that scatter light, his design uses mirrors that gather it. Light does not pass through, it reflects and folds back, concentrating starlight into a brighter image. The principle is simple. The more light you collect, the farther you see. But in their hands, that principle becomes almost poetic. The faintest glimmer from the farthest reaches of space is drawn inward, like a note being echoed in a concert hall. When the first of their great mirrors is finally complete, they carry it into the garden and assemble it under the open sky. The night is cold enough to sting their breath. Above them stretches the same endless darkness that diggers once imagined, no longer a ceiling, but a sea. William points the telescope upward. The eyepiece trembles slightly under his hand. Then, for the first time, he sees what no one before has truly seen, the Milky Way as a landscape. Through the telescope, the hazy band that crosses the sky resolves into countless pinpoints of light. The Milky Way isn't a mist or vapour. It's a collection of stars so numerous that they blur together. It's as though the night sky were a great city seen from far above, every home with its own candle. William and Caroline begin to record what they see, charting the positions of stars, clusters, and faint cloud-like shapes. They work for years, mapping the heavens one small patch at a time. Each observation feels like a heartbeat in a grand symphony of discovery. In 1781, during one of these long nights of observation, William notices something different, a small disk of light that moves slightly against the background stars. It's not a star at all, but a planet. He has discovered Uranus, the first new planet found since ancient times. The world celebrates him, and he becomes the king's astronomer. Yet the discovery is almost a distraction. What he wants more than fame is understanding, so he keeps mapping. Each sweep of the telescope reveals more than the last. He and Caroline note that the stars are denser in one direction, the band of the Milky Way, and thinner toward the edges. From this they begin to infer the shape of our galaxy, a vast flattened disk, like a great luminous wheel. At its apparent centre, William places the Sun. It seems reasonable. After all, it's the star we know best. But it's a mistake, a gentle one. We're not in the middle of the Milky Way, just one bright dot on its edge. Still, even that misunderstanding is beautiful, because it shows a truth about our minds. We begin every map with ourselves at the centre until the universe teaches us humility. Their work is exhausting. Caroline later writes that some nights they work until dawn, their breath freezing in the air as they take turns at the telescope. When the cold becomes unbearable, they warm their fingers over the lamp and continue. Sometimes the mirror fogs over, and they wipe it with soft cloths before returning to the eyepiece. They are explorers, but their ocean is light. As they continue, they notice something else. Beyond the stars of our galaxy, there are faint glowing clouds that never resolve into single points of light. No matter how powerful the telescope, these smudges remain misty and undefined. William calls them nebulae, from the Latin for clouds. He believes they are swarms of stars or clusters of gas within our own Milky Way, but he can't be sure. Some part of him suspects they might be entire systems of stars, separate and distant. In a letter, he He writes that the universe is full of islands of light, perhaps beyond counting. It's a thought as daring as Diggis's infinite sky. If true, it means that even our galaxy, enormous as it is, could be just one island among countless others, a single note in an unending composition. Caroline discovers nebulae too, and dozens of comets. Her contributions are precise and vital, yet in her lifetime she's often overlooked. Still, she keeps her brother's logs and measurements, helping him turn data into meaning. Together they create the first rough map of the Milky Way, a drawing that looks almost like a whirlpool, dense with light at the centre and tapering into darkness at the edges. It's easy to imagine the two of them pausing after a long night, standing outside in the frosty dawn, their tools scattered around them. The sky above is pale now, but they know what lies behind it. Billions of stars, each burning quietly in the great turning disk of the galaxy. The music of their instruments, once meant for concert halls, has become the music of the cosmos itself. By the end of the 18th century, thanks to their work, humanity finally has a sense of the shape of our home. Not a flat ceiling, not an infinite abstraction, but a structure with depth and form, a spiral of stars with its own geometry, its own quiet rhythm. The Herschel's telescopes turned curiosity into a craft and craft into revelation. From here, the story opens outward again. Others will take up the same question that haunted William and Carolyn. How far does the starlight go? To find the answer, humanity will learn to measure not with mirrors or metal, but with light itself, a rhythm written across the hearts of certain stars. And so the next stage of the journey begins, with a woman whose quiet persistence will teach us how to read the distances between suns. The map of the heavens was growing. William and Caroline Herschel had revealed its shape, a glowing, flattened disk of stars, but no one yet knew how large that disk truly was. The sky, after all, is like a painting without scale. The stars look close together, yet they might be scattered across distances so immense that light itself takes centuries, even millennia, to pass between them. Humanity had drawn the outlines of the cosmos, but the numbers behind it were still guesses, and the space between stars remained a mystery too vast to touch. For centuries, astronomers had wondered, how far away is a star? If the stars are like the sun, just smaller and farther off, there must be some way to measure their distance. But how do you measure something so remote that even its light seems untouchable? The key would come from a very simple trick, one that every child knows without realizing. If you hold up your finger and look at it with one eye, then the other, it seems to shift slightly against the background. That tiny difference, that small jump from one viewpoint to another, tells your brain how far away it is. This is how we sense depth. Our two eyes, set apart, give us two perspectives. The greater the shift, the closer the object. The smaller the shift, the farther it must be. Now imagine using the Earth itself as a pair of eyes. As our planet orbits the Sun, it moves from one side of its path to the other, about 300 million kilometers apart. If we photograph a nearby star in January, and then again in July, we should see that same small shift against the background of more distant stars. That shift, called parallax, could reveal how far away the star truly lies. It sounds simple, but in practice it is almost impossible. The stars are so far that the shift is smaller than the width of a human hair seen from kilometers away. For centuries, astronomers tried to detect it, but their instruments were too crude. The heavens appeared fixed, and many gave up, thinking the stars were infinitely distant after all. Then, in the early 19th century, a quiet, meticulous German astronomer named Friedrich Bessel decided to try again. He was patient in a way that most people could never be, willing to spend years staring at the same patch of sky, measuring, correcting, and measuring again. His chosen target was a faint double star in the constellation Cygnus, known today as 61 Cygni. It wasn't beautiful or bright, but Bessel suspected it might be close enough for his method to work. Night after night, through cold and fatigue, he recorded its position, comparing it to more distant stars that served as a backdrop. His tools were far better than those of the past, precise micrometers and telescopes that could detect the smallest motions, and slowly, over the course of months, he began to see it, a tiny rhythmic shift. The star wobbled slightly against the background as the Earth moved in its orbit. It was the faintest tremor of parallax, but it was enough. Using that tiny angle, less than 1 second of arc, a fraction of a degree, he calculated the distance. 61 Cygni, he found, lay about 10 light-years away. In more human terms, its light had been travelling toward us for a decade before it reached his telescope. For the first time in history, someone had measured the distance to a star. The sky was no longer a flat ceiling of pinpoints. It had depth, dimension, and scale. Humanity had learned to measure the unreachable. Of course, the number itself was almost beyond comprehension. A light-year is about 10 trillion kilometres. Even the nearest star is unimaginably far. To travel that distance at the speed of an airplane would take more than 30 million years. Yet what mattered was not the number, but the proof. The universe had become three-dimensional. The stars were no longer fixed jewels on a dome. They were suns, scattered through an ocean of space. Bessel's discovery inspired others to refine his technique, to measure more and more stars. But parallax has its limits. Even with the most careful observations, it works only for the closest suns, the ones near our galactic neighbourhood. The vast majority of stars remain far beyond its reach, their distances invisible to geometry alone. It would take new minds and new methods to go farther, to learn to measure not just the position of a star, but its heartbeat. Someday soon, someone would find a way to turn light itself into a ruler, to read distances from brightness and time. But before we drift there, it's worth pausing for a moment with Bessel. Imagine him in his cold observatory, the faint ticking of his clock marking each careful measurement. His lamp burns low, the air smells of ink and metal. Outside, snow muffles the world. Inside, the universe is unfolding one tiny angle at a time. There's something almost sacred in that image, a single human being using patience as his telescope, measuring eternity through fractions of light. He cannot yet know how vast the cosmos truly is, but he has opened the first door. Others will follow, and each will carry the same quiet faith, that even the most unreachable truths can be drawn a little closer if you listen long enough to what the stars are trying to tell you. As time moves forward, so will our instruments. The dusty workshops of the past will give way to glass plates, electric light, and the first photographs of the sky. The stars will no longer just be seen, they'll be recorded, measured, and compared. And soon, in one of those quiet rooms filled with glass and silence, another kind of rhythm will be discovered. The heartbeat of the cosmos itself, pulsing in the light of distant suns. Our quiet journey now moves from the age of brass telescopes and burnt fingertips into the era of glass and light. The 19th century fades into the 20th, and the stars begin to be captured not by eyes alone, but by the patient memory of photographic plates. The observatory becomes a strange new kind of workshop, a place where time itself can be bottled, light frozen into thin glass squares that will wait years to be read. And in one of these quiet rooms at Harvard, a woman named Henrietta Leavitt sits among the stars, not in the heavens but spread out across her desk. The room is dim. The windows are sealed against the New England cold. The walls are lined with shelves stacked high with glass negatives, thousands upon thousands of faint dots and smudges. Each plate holds a fragment of the night sky, taken through telescopes far to the south in Chile, where the air is clear and the stars are bright. The light from those stars has travelled for hundreds or thousands of years, only to end its journey here in Henrietta's hands. She's one of the Harvard computers, a group of women hired to measure and catalogue the heavens. The word computer once meant a person, not a machine. Someone whose mind could perform slow, careful miracles of calculation. Henrietta works quietly, methodically, marking each star's brightness and position. Her handwriting is neat but small, as though she's afraid to leave too much of herself among the stars. One evening, while studying a set of variable stars in the Magellanic Clouds, two faint ghostly galaxies that drift near our own, she begins to notice something. Some of these stars pulse with a steady rhythm. Their light brightens, fades, then brightens again, as if they are breathing. The rhythm is regular, like a cosmic heartbeat, and the slower the beat, the brighter the star seems to be. The faster it flickers, the dimmer it truly is. It's a simple pattern, yet astonishing. The rhythm of a star's pulse tells you its true brightness, and if you know how bright something truly is, you can compare it to how faint it appears and calculate its distance. In this way, light itself becomes a ruler, stretched across the vast emptiness of space. Henrietta writes up her results quietly, without grand claims. She doesn't have the authority to use the telescopes herself. At that time, women at the observatory aren't allowed to. She simply publishes her findings under the modest title, Periods of 25 Variable Stars. But that paper, and the patient mind behind it, will give humanity its first real measure of the universe. Years later, across the continent and high in the mountains of California, another astronomer is chasing a very different dream. His name is Edwin Hubble, and unlike Henrietta, he loves spectacle. He speaks with a deliberate English accent that isn't truly his own. He wears a fedora even in the observatory dome and carries himself like a man who knows the world will listen. Yet beneath that confidence lies a deep curiosity, the same quiet hunger that once kept Henrietta awake among her glass plates. Hubble works at Mount Wilson Observatory, home to the world's largest telescope at the time. Its great silver dome crowns the mountain like a metallic moon. Inside, the 100-inch mirror gathers starlight from across the universe, focusing it into sharp images on photographic film. Hubble spends long nights up there, adjusting gears and guiding the telescope by hand as it tracks the sky. He turns his attention to a faint smudged patch of light in the constellation Andromeda. For centuries, people have seen it through smaller telescopes, calling it a nebula, a cloud perhaps within our own Milky Way. But no one really knows what it is. Some think it's a small cluster of stars not far away. Others whisper that it might be something much larger, a galaxy like our own, far beyond the Milky Way's edge. Hubble begins taking long exposures of Andromeda, collecting light for hours at a time. Each image is developed on glass plates which he inspects under a magnifying lens. He's searching for any star within that cloud that changes in brightness, one that pulses with a rhythm like Henrietta's Cepheids. If he can find one, he can use her relationship between brightness and period to determine the object's distance. Weeks pass. Then, one night, while comparing plates, he sees it. A single star that has brightened and dimmed in perfect rhythm. In the margin of the plate he scrawls a single word, var, short for variable. That small mark becomes one of the most important notes in the history of science. Using Henrietta's law of brightness and rhythm, Hubble calculates how far away the star must be. The result is staggering. It's not within our galaxy at all. It's millions of light years beyond it. Andromeda is not a cloud inside the Milky Way. It's another galaxy altogether, a vast island of stars, each with their own suns, their own potential worlds. The universe has just expanded beyond imagination. Until that moment, most astronomers believed the Milky Way was the entire cosmos. Now, with one discovery, that idea collapses. The sky we thought we understood becomes an ocean of galaxies, each one swirling like a giant whirlpool of light. Our own galaxy is only one island among billions. It's hard to overstate how shocking this was. For centuries, humans had drawn smaller and smaller circles around themselves, each one expanding our sense of place, from Earth to the solar system to the Milky Way. Now the circle has no edge. Everything we know floats in an unimaginable sea. When Hubble presents his findings, even the great Albert Einstein visits him at Mount Wilson. Standing beside the enormous telescope, Hubble shows him the photographic evidence of galaxies retreating into the dark. The light from these galaxies is stretched toward the red end of the spectrum, meaning they are moving away. Space itself is expanding. Einstein, who had once resisted the idea, smiles faintly and admits what he calls his greatest blunder, trying to keep the universe still in his equations when it was never still at all. From Henrietta's quiet desk to Hubble's mountain dome, a single thread connects their work: the language of light. The stars speak it fluently. We've only just learned to listen. If you step outside on a clear night and look toward the faint smear of Andromeda, you're seeing light that began its journey 2.5 million years ago. Long before cities, before history, before we had words for wonder, that light was already on its way. It crossed the abyss, untouched, until it reached the small eyes of a creature that had only just begun to understand what the sky truly was. And somewhere, perhaps, that's the real meaning of discovery. Not the expansion of maps or the accumulation of facts, but the quiet realization that the light has been waiting for us all along. As our story drifts onward, the questions grow deeper. If the universe is expanding, what is it expanding into? What is this space that stretches, this invisible stage on which everything moves? The path now bends toward a new mystery, the shape of the invisible itself. What is space? It seems like such a simple question, the kind a child might ask while lying on their back and tracing clouds across the sky. You might say space is nothing. It's what's left when everything else is gone. But that answer, like so many in science, only opens the door to deeper mysteries. For most of human history, space was seen as a kind of stage, a background on which the drama of planets and stars played out. It was silent, empty, and still. But over time, scientists would come to realize that space itself might have a shape, a rhythm, and even a life of its own. To understand how that idea began, we need to step back to a world drawn with perfect lines and flawless symmetry, the world of Euclid. More than 2,000 years ago, Euclid wrote The Elements, a book of geometry that would become the quiet language of space for millennia. It was a universe of order, parallel lines never meeting, triangles whose angles always added up to a perfect 180 degrees. Every builder, navigator, and thinker lived within its neat geometry. Even the heavens, they believed, followed its rules. For centuries, Euclid's geometry felt unbreakable, as natural as gravity itself. But slowly, cracks began to appear in that certainty. On the curved surface of the Earth, explorers noticed strange distortions. Ships following straight courses would meet again after circling the globe. Lines that should never cross did. The world wasn't a flat canvas after all, it was a sphere. One of the first to see the deeper meaning of this was Carl Friedrich Gauss, a quiet German mathematician with a mind as sharp as sunlight through glass. Gauss was fascinated by the idea that a surface could be curved and yet exist completely within itself. You didn't need to look from outside to see the curve. You could feel it from within. Imagine, he said, an ant walking on a balloon. The ant doesn't know the balloon is round, but it can measure the distances between its steps, the way triangles and circles behave, and realize that the world beneath it must be curved. From this simple thought came a radical insight. The rules of geometry might not be fixed. Space could bend, stretch, or curve, and if it did, the paths of everything moving through it, light, planets, even time, would change. After Gauss, another mind carried the idea further. His name was Bernhard Riemann, and his imagination lifted geometry from paper into possibility. He imagined spaces of any shape, curved not just like a globe, but in ways impossible to visualize, like folds upon folds, dimensions curling within themselves. His mathematics described space not as a rigid container, but as something that could twist and ripple, perhaps even flow. Of course, in daily life, the world still feels flat. When you place a cup on a table or walk across the floor, there's no sense of curvature. But imagine spreading a thin sheet of cloth and setting a small ball in the centre. The fabric dips slightly under the weight. If you roll another ball nearby, it naturally drifts toward the first, not because they attract each other, but because the fabric itself slopes. That image, which Riemann's mathematics would one day make possible to describe precisely, became the foundation for understanding gravity as more than a force. Centuries earlier, Isaac Newton had explained gravity as an invisible pull between masses. His equations worked beautifully, but left one haunting question unanswered. How could one object reach across empty space to tug on another? He didn't know. He simply accepted that the universe worked that way. Riemann, and those who came after him, suggested something bolder. Maybe there was no invisible hand reaching across the void. Maybe the space itself carried the message. You can imagine Riemann's world of curves as an ocean with invisible currents. A ship crossing it may think it's steering straight, but the sea beneath it flows, bending its path ever so slightly. In that sense, gravity might not be a command shouted across emptiness, but a whisper from the shape of the world itself. When Riemann first proposed this new geometry in 1854, it was almost too strange for anyone to grasp. Even his audience of scholars sat in silence, unsure what to make of his idea that space could have its own curvature. To them, it sounded more like poetry than physics. It would take another 50 years, and one curious patent clerk with a mind full of questions to turn that poetry into reality. That clerk, of course, was Albert Einstein. But before we reach him, let's stay for a moment with the beauty of Riemann's idea, the simple yet profound thought that space doesn't need anything outside itself to bend. It can curve purely because of the things within it, the way a sail fills when wind moves through it. You don't see the wind, only the curve it creates. And maybe, in the same way, we don't see the shape of space, only the way it carries light, matter, and time. Even now, if you look up at the night sky, the stars appear scattered on a flat black canvas. But the truth is far subtler. You're standing on a small sphere of rock, turning through the curvature of a larger spiral of stars, itself bent within the broader geometry of the cosmos. Every photon that reaches your eyes has travelled along the contours of that invisible shape. It's humbling to think that every movement, from the fall of an apple to the drift of galaxies, may simply be the result of the universe's geometry guiding its own contents. We are passengers in a sea whose waves are made not of water, but of space itself. As this realization dawned, the idea of emptiness would begin to fade. The universe was no longer a hollow container. It was a fabric, a surface, a field alive with motion. And from this new vision, one man would compose a theory so elegant that even he described it as the most beautiful of thoughts. Our quiet exploration now turns toward that man, sitting in a small room in Bern, Switzerland, surrounded by letters and clocks. His name is Albert Einstein, and soon he will show that space and time are not separate notes, but parts of a single, cosmic melody. Picture a man sitting alone at a cluttered desk in a small apartment in Bern, Switzerland. The room is filled with the faint ticking of clocks, dozens of them, some dismantled, others repaired, a few running slightly out of sync. Outside, the trams clatter along the cobblestones. He's 26, wearing a wrinkled suit and a look of quiet absorption. This is Albert Einstein, a patent clerk by day, a dreamer of the cosmos by night. His job is to read inventions, machines designed to measure time with perfect precision. And yet, what he is really trying to measure is something much larger: time itself. He has always distrusted authority, even the invisible kind. To him, the universe is not a grand hierarchy ruled by mysterious forces. It is a pattern waiting to be understood. He begins to suspect that time and space, though supposedly separate realms, might be part of one continuous whole. He will later call it space-time, but for now it exists only as a melody in his mind, a harmony waiting to be written down. Einstein knows the work of Gauss and Riemann, the idea that space could bend like a sail in the wind. He knows Newton's picture of gravity too, a pull reaching across emptiness. But something about Newton's universe feels incomplete, like a beautiful song missing its final chord. If gravity truly acts at a distance, with no medium, how does one object know where another is? What invisible messenger carries the message of motion through the void? As he thinks about this, he imagines an elevator in free fall. If you were inside, floating as the elevator drops, you wouldn't feel your own weight. You would drift as if in deep space. To Einstein, that simple thought experiment is a revelation. Gravity and motion are not opposites. They are twins. What we feel as weight is just our resistance to the natural curvature of motion. Now he begins to see the world differently. The apple that fell on Newton's head was not being pulled by some invisible string. It was simply following the natural curve of space around the Earth. The apple wasn't falling. It was resting on the smooth slope of space-time, sliding along the shape carved by the planet's mass. Gravity isn't a tug, it's geometry. This realization is the beginning of his general theory of relativity. But he does not think in symbols or equations. He thinks in pictures. He imagines light rays bending around the sun, time itself slowing near massive objects, and space behaving like an enormous flexible fabric. The heavier the object, the deeper the curve. If you could see gravity, it would look like a dance. Planets circling stars, not because they are leashed, but because they are gliding through a cosmic whirlpool of curved space-time. Einstein works through these ideas slowly, patiently, scribbling equations on scraps of paper, muttering to himself. His desk is messy, but his thoughts are symphonic. When he finally publishes his theory, it feels less like a discovery and more like a composition, something that had always been there, waiting to be heard. He writes that matter tells space how to curve, and space tells matter how to move. It's a simple sentence, but it changes everything. The universe is no longer a static stage with actors moving upon it. It's a living choreography, every step influencing the dance floor beneath it. The planets curve space, and that curvature guides their paths in return. A few years later, his idea will be tested. During a solar eclipse in 1919, when the moon blocks the sun's glare, astronomers measure the light of distant stars passing near the sun's edge. According to Newton's laws, the light should pass straight. According to Einstein, it should bend slightly, following the curve of space itself. When the photographs are developed, the starlight appears shifted just as Einstein predicted. Space, it turns out, truly bends. The headline the next morning reads, "Revolution in Science, New Theory of the Universe." But fame sits uneasily on him. When reporters ask how it feels to be the smartest man alive, he shrugs and says, "I am merely curious." He plays the violin at night, losing himself in Bach and Mozart, his fingers tracing notes that sound almost like the quiet equations running through his head. The melodies remind him that beauty and truth, in their purest forms, are often the same thing. The idea of curved space is difficult to picture, yet the way to feel it is simple. Imagine standing on a trampoline. When you step in, the fabric sags. Roll a ball nearby, and it circles you, following the dip. That's how the Earth holds the moon, and the sun holds the planets. The stage of the universe is not flat, it's elastic. Every object, every bit of energy, changes its shape slightly. Even light, which was once thought to travel straight through nothing, must follow the contours of this fabric. And what about time? In Einstein's picture, time is not a steady rhythm ticking the same everywhere. It slows in the presence of gravity. The closer you are to something massive, the more time stretches. A clock on a mountain runs slightly faster than one in a valley. The difference is tiny, fractions of a heartbeat, but it's real. In a sense, gravity is not just the bending of space, but the bending of time itself. Think of it as a slow waltz between the two. When space bends, time leans. Together they form the rhythm that governs the cosmos. From the spin of galaxies to the fall of a raindrop, everything moves in step with that quiet tempo. Even today, every GPS satellite orbiting above you must account for this subtle shift in time, adjusting its clock so that your phone can know where you are. Einstein's ideas aren't abstract, they're woven into the daily hum of the world. But for Einstein himself, the joy was never in the practical outcome. It was in the elegance, the way a few simple principles could explain the behaviour of the entire universe. His theory showed that space wasn't a void after all, but a living structure, responsive and full of quiet motion. It was as though the universe had revealed a secret melody, one that had been playing beneath the noise all along. As we drift further into the story, that melody will expand. The curved fabric of space-time will begin to stretch, as if inhaling. The universe, once thought eternal and still, will take its first great breath, and everything we see today will ride on that expanding rhythm, the gentle pulse of creation itself. Einstein's new picture of space and time was beautiful, so beautiful that even he hesitated to believe all that it implied. His equation suggested that the universe couldn't sit still. Space itself wanted to move, to stretch or shrink, like the surface of a balloon being filled with air. Yet Einstein couldn't quite accept that. To him, the universe felt eternal and balanced, more like a great cathedral than a living, expanding sea. So to keep the cosmic structure from collapsing or flying apart, he added a small correction, a kind of mathematical counterweight he called the cosmological constant. It was meant to hold the universe in place. He thought of it as a necessary adjustment, a patch to preserve harmony. But in time, the universe would show him that harmony didn't mean stillness, it meant motion. In the early decades of the 20th century, astronomers around the world were building ever larger telescopes. The most powerful of them all stood high on Mount Wilson in California, where the night air was thin and steady. There, Edwin Hubble, tall, theatrical, and meticulous, used the giant telescope to peer deeper into the darkness than anyone before him. He photographed the faint smudges of distant galaxies, each one an island of stars, their light so faint it had been crossing the void for millions of years. When he studied that light carefully, he found something strange. It was stretched. Its colour shifted toward the red end of the spectrum, as if the galaxies were moving away from us. The farther the galaxy, the greater the stretch. Hubble at first thought it might be an error, but the pattern was too precise to ignore. Every direction he looked, galaxies were receding. In music, when a note is stretched, its pitch lowers, its sound deepens. In light, the same thing happens. The waves lengthen as the source moves away, turning from blue toward red. It is called redshift, but you don't need to know the term to feel its meaning. The universe was expanding. Space itself was swelling, carrying galaxies with it like dots on the surface of an inflating balloon. When Einstein heard of Hubble's results, he realized that his correction had been unnecessary. The universe was already in motion. He had tried to keep it still, only to discover it had been breathing all along. Later, he would call the cosmological constant his greatest mistake. But in a way, it was a kind of humility disguised as error, an admission that the universe did not need his permission to move. To picture what Hubble found, imagine you're standing on a vast rubber sheet sprinkled with confetti. If you stretch, the sheet from every side, each piece of confetti moves away from every other, not because it's flying through space, but because the space between them is expanding. There is no central point of explosion, no single spot where everything began. Every point is receding from every other. To every observer, the universe appears to be moving away, equally and everywhere. It's a difficult idea to hold in the mind because we're used to things expanding into something. When a balloon inflates, it fills the air around it. But the universe isn't expanding into a larger space. It's the space itself that grows. There is no outside, no edge, no empty void beyond. The cosmos is all there is, and it is stretching itself thin, like the slow rise of dough in an infinite oven. This vision transformed everything. The universe was not a timeless monument, but a dynamic process. If space is expanding now, that means it was once smaller. Follow that logic backward, and you arrive at a moment when everything, the stars, the galaxies, all the atoms in existence, was compressed into a state so dense and hot that the laws of physics as we know them dissolve. That first moment would later be called the Big Bang, though it was not an explosion in space but an expansion of space. You can almost hear it as a breath, the long, slow inhale of existence. From an unimaginably small beginning, the universe began to stretch, cooling as it grew. Light separated from matter, hydrogen and helium formed, the first simple elements. Gravity gathered them into clouds, and those clouds collapsed into stars. And within those stars, heavier elements were forged. The carbon in your cells, the iron in your blood. Every atom in your body once drifted in that primal breath. Einstein's equations, once meant to describe the quiet curvature of space, had become a kind of creation story. Space-time was not a stage, it was a living, changing fabric, woven from the same threads as everything else. The cosmos was not sitting still, it was unfolding, moment by moment, into itself. It's strange to think that even now, their expansion continues. Every second, the space between galaxies stretches a little more. Light travelling across the universe carries with it a record of this expansion, like a violin string slowly detuning over billions of years. What began as brilliant blue light becomes red, then infrared, then invisible. The song of the cosmos is always slowing, its notes drifting into deeper silence. And yet, in that silence, there is music still. The fact that the universe expands means that time itself has direction. There is a before and an after, a sense of movement, of breath. Without that motion, there would be no change, no stars, no life. To exist at all is to be carried along in this quiet exhalation. For Einstein, this realization was bittersweet. His universe, once eternal and balanced, had become transient, alive and ever-changing. But there is something profoundly comforting in that change. It means the cosmos is not a cold mechanism, but a story, one that began long before us and will continue long after, a story written in the language of light and expansion. As we drift further into that story, we begin to follow the light itself backward, tracing its journey through the ages. If the universe is expanding, then its past must still echo around us, faint and ancient, like the aftersound of a note long played. That echo, hidden in the background of everything, is the whisper of creation itself, a soft radiation still filling the night, long after the first breath of the universe was taken. If you could somehow turn back time, winding the expansion of the universe in reverse, everything would draw closer together, the galaxies, the stars, even the smallest atoms, until the cosmos itself became a single glowing storm of energy. But although we can't rewind the universe, we can still listen for the echoes of that beginning. Somewhere out there, faint but persistent, the first light is still travelling. For a long time, astronomers believed the universe might be infinitely old, that it had always been expanding or contracting, always breathing in some eternal rhythm. But as they looked deeper, they began to find evidence of a definite beginning, a moment when light first separated from matter and began its long journey through space. That ancient light still moving today is known as the cosmic microwave background. It is not light you can see with your eyes. By the time it reaches us, it has cooled, stretched by billions of years of cosmic expansion, until it is more like a whisper of warmth than a visible glow. It fills every corner of the sky evenly, a perfect fog of ancient radiation. It is the afterglow of creation, the universe's first light still shining, though dimmed to a murmur. To imagine what this looked like, picture the early universe not as an explosion, but as a thick mist of particles. For its first 380,000 years, the cosmos was hot and opaque, a sea of light and matter so dense that photons, the particles of light, could not travel freely. They were constantly scattered, bouncing between atoms like children in a crowded room. Then, as the universe expanded and cooled, the fog began to lift. At that moment, light broke free. The first photons began to move unhindered through space, and they have never stopped. Today, those same photons wash over us from every direction. They are everywhere, passing through clouds, drifting through walls, even gliding across your skin as you listen to this story. You can't see them, but if your eyes could detect microwaves instead of visible light, the night sky would glow softly and evenly. You would be looking at the universe as it was almost 14 billion years ago. The discovery of this faint light happened almost by accident. In 1964, two engineers, Arno Penzias and Robert Wilson, were testing a large antenna built for radio communication. No matter where they pointed it, they picked up a persistent hiss, a background noise that wouldn't go away. They cleaned the antenna, even chased away a family of pigeons nesting inside, but the hiss remained. They didn't realize at first that they had stumbled upon the oldest sound in existence, the afterglow of the Big Bang. Elsewhere, a team of astrophysicists had already predicted that such a signal should exist, a faint radiation filling the universe, the residue of its first light. When they learned of Penzias and Wilson's strange noise, they recognized it immediately. The hiss was not interference at all. It was the cosmic background itself, the hum of creation still echoing through time. When that light first began its journey, the universe was unimaginably young. Its glow was white-hot, its brightness beyond any star we know. Over billions of years, as space expanded, the light stretched and cooled, its colour shifting from blinding blue to soft red to invisible warmth. The same way a note lowers in pitch as it echoes down a long corridor, this light's wavelength lengthened as the universe grew. Now it hums at a frequency far below visible light, a cosmic lullaby, still playing after nearly 14 billion years. This light tells us more than just the age of the universe. It carries a faint pattern, tiny ripples in temperature, differences as small as 1 part in 100,000. These subtle irregularities are the fingerprints of the early cosmos, the seeds from which galaxies, stars and planets would grow. Every cluster of galaxies, every spiral of starlight, every world that would one day cradle life, all of it traces back to the gentle unevenness frozen in that ancient light. You can think of it like the grain in a piece of wood. Even if you sand it smooth, the pattern remains, guiding where cracks might form, where lines might curve. The universe began not in perfect symmetry, but in a slightly uneven one, and that imperfection was the blueprint for everything that followed. Astronomers have mapped this cosmic background in exquisite detail. Satellites like COBE, WMAP and Planck have scanned the entire sky, measuring the faint temperature variations with stunning precision. When the data is turned into an image, it looks like a mottled, softly coloured sphere. Speckles of blue and orange, delicate as the surface of an ancient shell. It is the earliest portrait we have of the universe, a baby picture taken before the first stars were born. And yet, despite all the complexity behind these discoveries, there is something deeply human about it. The light we study today is the same light that once illuminated the birth of all things. It has crossed every era of cosmic history to arrive here, faint but faithful. To listen to it is to listen to the memory of existence itself. If you close your eyes, you might imagine that faint hiss, like static on an old radio, the sound between stations. That sound is not just noise. It is the universe speaking in a language older than stars. Every photon carries a story, a record of temperature, density, motion, a diary of the cosmos written in the ink of light. Even now, this ancient glow wraps around you, filling every room, every breath of air. The warmth you feel from it is so subtle you wouldn't notice, yet it is everywhere, constant and kind. The universe has never truly gone dark. It only dimmed as it aged, like a lantern burning low but never extinguished. It's strange, isn't it? We search the night for light, not realizing that it already surrounds us, invisible and eternal. Every moment, the echo of creation drifts quietly through us, a reminder that even in the coldest emptiness there is memory, light that never stopped travelling, light that never stopped becoming. As we follow this light deeper into its journey, we begin to wonder where it's all leading. The universe began with brightness, but will it end that way? Or will it fade into silence, the stars slowly dimming until only the dark remains? Our story now turns toward that distant future, a future written not in explosions but in the soft retreat of light into memory. If the early universe was a burst of fire and brightness, then the far future will be its mirror image, a long, slow drift into quiet. The light that once blazed will thin, the stars will fade, and the cosmos will return to something like stillness. Not the stillness of peace exactly, but the slow exhale of everything that ever was. When astronomers first realized that the universe was expanding, they naturally wondered what would happen next. Would gravity, the great sculptor of galaxies, eventually slow the expansion and pull everything back together in a final collapse? Or would the expansion continue forever, spreading matter thinner and thinner until even light could no longer find company? For decades, the balance between those two possibilities, rebirth or emptiness, was unknown. Then, in the late 1990s, two teams of astronomers set out to measure how the universe's expansion was changing over time. They studied distant supernovae, exploding stars that shine with almost uniform brightness. Because we know how bright these stellar outbursts truly are, we can use their apparent faintness to estimate distance, like reading the wattage of a lamp across a dark room. These explosions are also cosmic clocks. The farther away they are, the older their light. By comparing distance and time, the scientists hoped to measure the universe's rate of change. The result was unexpected, almost absurd. Instead of slowing down, the universe was speeding up. The expansion was accelerating. The galaxies weren't merely drifting apart, they were being pushed away faster and faster, carried by something unseen. That invisible driver came to be called dark energy. No one knows exactly what it is, though the name makes it sound mysterious. It's not a substance, not a wind or a force that can be felt. It is more like a property of space itself, a quiet pressure woven into the very fabric of the cosmos. The larger the universe becomes, the more space there is for this subtle energy to act, gently stretching everything apart. To visualize it, imagine painting tiny dots on the surface of a balloon. As the balloon inflates, each dot moves away from every other, not because it's travelling across the surface, but because the surface itself is expanding. Now imagine that the balloon never stops growing. The farther the dots get from each other, the faster they appear to recede. That's how our galaxies behave. The space between them is swelling like a tide that never turns. Over immense timescales, billions upon billions of years, this quiet stretching will reshape the night sky. Distant galaxies will slip beyond the horizon of visibility. Their light, stretched to longer and longer wavelengths, will fade into nothingness. Even the cosmic background, that ancient whisper of the Big Bang, will thin until it is undetectable. The universe will become a lonely archipelago of isolated galaxies, each surrounded by a growing sea of darkness. And it won't stop there. Within each galaxy, the stars themselves will begin to die out. The largest, brightest ones will live fast and burn out first, exploding in grand farewells that leave behind neutron stars and black holes. The smaller, steadier ones, like our Sun, will last far longer, but even they will eventually run out of fuel. When the Sun reaches that point, it will swell into a red giant, shedding its outer layers in waves of shimmering gas before collapsing into a small, dense ember, called a white dwarf. Billions of years later, those white dwarfs will cool until they are completely dark, cold cinders scattered through an ever-expanding void. Planets will drift silently around extinguished suns. The cosmic furnace that once blazed with countless lights will dim, then darken. But even then, the universe will not be entirely still. Black holes will continue to stir, swallowing the remnants of stars. For a while, they will dominate, the only major actors left in the cosmic play. Yet even black holes are not eternal. As Stephen Hawking showed, they slowly leak energy, radiating heat so faint it takes longer than any human time to imagine. Over unimaginable epochs, they too will dissolve into the fabric of space, releasing their last whispers of light. If you could stand at that distant future, trillions upon trillions of years from now, you would see a universe emptied of structure. No galaxies, no stars, only faint traces of radiation, scattered particles, and the slow hum of expanding space. The temperature everywhere will approach absolute zero, the point where motion nearly stops. It is called the heat death of the universe, though it is more a cooling, a final settling into equilibrium. It sounds bleak, but there's something strangely peaceful in this vision. The cosmos, having rushed from its brilliant birth, will come to rest in silence. All the matter and light that ever existed will have done their work, forged stars, built worlds, given rise to thought, to wonder, to life itself. The great expansion that began as a breath will end as a sigh. And yet, even that quiet might not be the end. Some cosmologists suggest that dark energy might one day grow stronger, tearing even galaxies and atoms apart in a final big rip. Others imagine that quantum fluctuations, the restless heartbeat of the vacuum, could ignite a new burst of creation somewhere else, a new universe budding from the ashes of the old. In this way, perhaps, the cosmos never truly ends. It transforms, forever reinterpreting its own melody. When you look up at the stars tonight, you're seeing them not as they are, but as they were, each one a note played long ago in this cosmic song. Every photon that reaches you is a traveller that has crossed vast gulfs of time and space, bringing a memory of brightness from the deep past. The stars we love most are already aging, already on their way to silence. But their light still reaches us, and in that light we glimpse eternity. So perhaps the universe's final act is not despair, but gratitude. It has spent itself in creation, and in doing so, made room for consciousness to exist. Beings who can look back and marvel, who can say, it was beautiful while it lasted. As our quiet exploration continues, the horizon of time folds inward. If everything is destined to fade, then what remains? What is space itself when it contains no stars, no light, no sound? From here, the story turns inward to the very nature of emptiness and to humanity's long, curious attempt to understand the meaning of nothing. Imagine holding a small wooden box in your hands. It's light enough to lift with one finger, smooth along the edges, perhaps with a faint scent of cedar. Now imagine opening it and removing everything inside, first the dust, then the air, then even the light. Suppose you could seal this completely so that no warmth, no sound, no single particle of anything could enter. What would be left? At first you might say nothing, but the word nothing is slippery. It sounds simple, yet it hides an entire history of misunderstanding. Human beings have always struggled to imagine emptiness. To our minds, every void must contain something, a whisper of air, a shadow, a thought, a presence. Even silence feels full. 2,000 years ago, the Greek philosopher Aristotle declared that a true vacuum could never exist. Nature abhors a vacuum, he said, meaning that the universe would rather tear itself apart than leave an empty space. To him, the void was unnatural, like a wound that the world itself would rush to fill. It was a comforting thought in a way, the idea that existence was continuous, that there were no gaps in being. Everything touched everything else, no emptiness, no isolation, and yet the idea of nothing refused to go away. It lingered like a question that could never quite be silenced. What happens, people wondered, if you try to make space truly empty? Would it collapse? Would air rush in to fill it, as Aristotle predicted? Or could you somehow coax nature into revealing a pocket of true nothingness? The problem was that for most of history we lacked the tools to find out. To make nothing, you first need to remove something, and until the 17th century no one could even remove air completely. When you opened a container, the atmosphere around you immediately flowed in, pressing invisibly on every surface. We live, as it turns out, at the bottom of a vast ocean of air, and its weight surrounds us constantly. Every moment it presses on your skin with the force of 100 kilometers of invisible water above your head. You don't feel it because the pressure inside you pushes back. Early thinkers tried all sorts of experiments to defeat this invisible sea. They built long glass tubes, metal pumps, and sealed chambers. They lit candles and watched them go out, not realizing that flame itself depends on air. Again and again, they failed. The world seemed to agree with Aristotle. Emptiness was impossible. The moment you tried to make it, nature filled it. But there is something stubborn about curiosity. It doesn't take impossible for an answer. For centuries, philosophers and alchemists dreamed of capturing a piece of nothing, as if by doing so they could hold the essence of the universe in their hands. One of them was an Italian scientist named Evangelista Torricelli, a student of Galileo. He began to suspect that the reason water pumps could only lift water to a certain height wasn't because of the pump, but because of the air pressing down on the surface of the water outside. To test this, he used something heavier than water, mercury, the silvery liquid metal that reflects light like a mirror. He filled a long glass tube with mercury, sealed one end, and turned it upside down into a bowl of the same substance. The mercury inside the tube fell slightly and then stopped, leaving an empty space at the top. That empty space was something extraordinary, a pocket where no air could reach, where nothing could be seen or felt. It was, as far as anyone could tell, a small fragment of true void. For the first time in human history, someone had made nothing. When Torricelli looked at that silent space above the mercury, he realized what it meant. The air around us has weight. It presses down on the mercury in the bowl, holding up the column inside the tube. The empty space above is not magic. It's simply the absence of air. We live submerged at the bottom of an ocean of air, he wrote, and in that single line the heavens seem to tilt. It's a beautiful irony to discover the weight of air, you must create a place without it. To understand the fullness of the world, you must first understand its emptiness. But before Torricelli, such an idea would have sounded absurd. Aristotle's words had lasted almost 2 millennia, and now, in a small laboratory lit by oil lamps, they were undone by a column of shining metal and a quiet pocket of nothing. From that discovery came a new kind of question, one less about philosophy and more about physics. If air has weight, then space above the atmosphere might be truly empty. Between Earth and the Moon, between the stars, perhaps the universe was not a solid crystal after all, but a vast void punctuated by matter. The night sky, once thought to be a perfect sphere filled with light, now seemed to hang suspended in a sea of emptiness. And yet that emptiness was no longer something to fear. It was a field of possibility. The same nothing that could exist in a glass tube could also stretch between planets, holding them in their delicate orbits. The vacuum had become real, and reality itself grew wider because of it. Imagine Torricelli looking at his experiment in the dim glow of evening, the mercury glinting like liquid moonlight. He cannot yet know how far this discovery will reach, that it will one day lead to air pumps, barometers, engines, and even spacecraft. All he knows is that the void exists, and it has changed everything. The world had taken its first step toward the understanding nothing, and as we drift gently onward, that curiosity continues. The next chapter of this story belongs to another experimenter, a man who will climb mountains to prove that air has weight, who will realize that emptiness is not rare, but the natural state of the universe itself. Picture a quiet workshop in Florence sometime in the mid-1600s. The air smells faintly of oil lamps and warm metal. On a table sits a long glass tube, one end sealed, the other open. Inside, a heavy silver liquid gleams in the flickering light. This is mercury, dense, reflective, and strangely alive as it moves. A man named Evangelista Torricelli stands over it, adjusting the glass with careful hands. He tips the tube upside down into a bowl of the same liquid, and something astonishing happens. The mercury inside slips downward, but not all the way. It stops, leaving a small empty pocket at the top. Torricelli watches it for a long time. That tiny gap, clear, silent, and untouched, refuses to fill. The world has always insisted that nature despises a vacuum, that emptiness must rush to close itself. But this gap does not close. It holds, as if the universe has paused there to think. What Torricelli has built is the first barometer, though he doesn't yet call it that. He has created a perfect measure of air's invisible weight. The height of the mercury inside the tube balances the pressure of the atmosphere pressing down on the bowl. The higher the air pressure, the higher the column of mercury climbs. The lower the air pressure, the farther it falls. The idea seems almost absurd at first. How could something as intangible as air have weight? You can't see it. You can't hold it. But the evidence stands gleaming in glass. The heavy mercury doesn't fall all the way down because the air above the bowl pushes against it with steady, invisible hands. It was a radical realization. We live beneath an ocean of air, and everything we do, every breath, every flicker of flame, is shaped by its pressure. Torricelli's discovery reached another brilliant mind not far away. Blaise Pascal, the French mathematician and philosopher. Pascal was fascinated by this strange notion of air as a kind of sea pressing on the world. If the weight of air holds the mercury up, he reasoned, then at higher altitudes, where there's less air above us, the column should fall lower. To prove it, he needed height. So, on a clear September morning in 1648, Pascal enlisted his brother-in-law, Florent Perrier, who lived near the Puy de Dôme, a mountain in central France. Perrier packed 2 mercury tubes and a team of helpers and began to climb. The villagers must have watched them with mild amusement, men trudging up the mountain, balancing fragile glass instruments as if carrying relics. At the base, Perrier measured the mercury column, about 76 centimetres high. Then he began the ascent, winding through cool forests, over damp stones, and into thinner air. The higher they climbed, the harder it became to breathe. When they reached the summit, they set the tube upright and watched the mercury slide lower, just as Pascal had predicted. That simple experiment carried out in the open air confirmed what Torricelli had hinted. The weight of the atmosphere decreases with altitude. Air presses hardest at sea level and eases as you rise, just as water pressure lessens the closer you swim to the surface. The invisible ocean of air had finally been measured, and its waves could be read like a tide. When Pascal heard the results, he was elated. "We live at the bottom of an ocean of air," he wrote, echoing Torricelli's poetic insight. That single sentence reshaped how humanity imagined its place in the world. The sky was no longer a realm of perfect weightless divinity. It was a physical substance, pressing, shifting, alive. The heavens had become part of nature's machinery, not its exception. It's humbling to think of that scene. Men on a mountaintop surrounded by clouds, watching a line of silver mercury fall by just a few centimetres and realising they were measuring the very breath of the planet. The difference was tiny, but its meaning was enormous. It proved that emptiness could exist, and that it didn't mean the end of things. It was simply what waited when the air grew thin. From that moment on, scientists began to treat emptiness not as a threat, but as a tool. They built vacuum pumps and glass spheres to test what happened when air was removed. Flames extinguished, bells fell silent, feathers and lead dropped at the same speed. Sound itself needed air to travel, light did not. Each discovery stripped away another layer of fear. The void was not chaos, it was clarity. The sky too changed in our imagination. What had once seemed a luminous ceiling became a vast expanse of air that faded into true emptiness. The stars were no longer fixed to a crystal dome. They were floating islands of fire in a sea of nothing. Humanity had, without realizing it, taken its first scientific step towards space. There is something deeply poetic in the idea that to reach the truth about emptiness, Pascal had to climb higher, to seek thinner air, to move closer to the void itself. The act of ascending became symbolic. The higher he went, the less the world pressed against him. The experiment was more than a measurement. It was a pilgrimage toward understanding. Later, Pascal would reflect not only on the physics, but on what it meant for the human spirit. He wrote about the infinite spaces that surrounded us, the silent immensity of the night sky, and the strange mixture of fear and wonder it inspired. "The eternal silence of these infinite spaces terrifies me," he confessed. Yet even in that fear, there was awe, a recognition that emptiness, once dreaded, was also beautiful. Today, when astronauts rise through the layers of atmosphere, they trace the same journey Pascal imagined. The air grows thinner, the mercury would drop lower, until finally it would vanish entirely. Above the clouds, beyond the faint blue glow of our sky, lies the same nothingness that Torricelli captured in a glass tube, a vast, endless vacuum that cradles the stars. But before humanity could reach it, we first had to believe it existed. The path from Aristotle's denial to Pascal's proof took 2,000 years. Yet it changed our understanding forever. The void was no longer a flaw in nature, it was part of its design. As our quiet journey continues, that realization deepens. If emptiness can exist on Earth and stretch across the heavens, then perhaps it is not mere absence. Perhaps it is something subtler, something waiting to be filled with light. And so we follow the next trail in this long story. The strange moment when scientists decided that even light itself must swim in a kind of invisible ocean, and how they discovered, at last, that the sea was never there. By the time Torricelli and Pascal had proved that air had weight, the world had changed forever. The heavens were no longer a crystal dome, but a thin atmosphere fading into emptiness. Humanity had finally accepted that space, true, silent space, could exist. But this raised another, deeper question. If the void was real, how did light move through it? Waves, after all, need something to wave in. Sound travels through air, rippling as vibrations between molecules. Ocean waves roll through water, pushing it gently forward. Even the trembling of a violin string must pass through wood and air to reach your ears. But light seemed to travel perfectly well through nothing at all. It crossed the gap between the sun and earth without slowing, burning across nearly 150 million kilometers of emptiness. How could that be? For scientists in the 18th and 19th centuries, the idea of waves without a medium felt impossible, so they imagined one. They called it the luminiferous ether, a beautiful phrase that means the light-bearing substance. It was supposed to be a kind of invisible ocean filling all space, weightless and undetectable, but everywhere at once. Light, they thought, was just the motion of this subtle sea, trembling like ripples spreading across a pond. It was a comforting picture. The ether gave the universe substance again, no longer empty but filled with a silent, transparent ocean that carried both light and gravity. It satisfied an old human instinct that the void must hide something deeper. For centuries, philosophers and physicists built theories upon it. They spoke of ether winds and ether tides, imagined that planets moved through it like fish through water. It was everywhere and nowhere, an unseen sea that no one could touch. But science, like light, moves restlessly forward. In the late 19th century, two American physicists, Albert Michelson and Edward Morley, decided to test the ether's existence directly. Their laboratory stood on a quiet street in Cleveland, filled with mirrors and lenses, polished brass, and a strange contraption that looked almost like a dream of geometry come to life. They reasoned that if the Earth was moving through this cosmic ocean, then the speed of light should change slightly depending on direction, just as a swimmer feels the difference between swimming with the current or against it. To test this, they built an instrument so sensitive it could detect differences smaller than a fraction of a wavelength of light. Michelson and Morley split a beam of light in two, sending the halves down perpendicular paths before recombining them. If the Earth was indeed drifting through ether, one beam should have taken slightly longer to return than the other. That difference would show up as a faint shimmer, an interference pattern. All they had to do was measure it. They waited. They turned their instrument slowly, repeating the experiment at different times of day, different seasons, hoping to catch the Earth moving through the invisible tide. But each time, they found nothing. The two light beams always returned in perfect harmony, no matter which direction they pointed. It was an unsettling silence. The ether wind didn't blow, the cosmic ocean didn't ripple. The experiment had revealed with delicate precision that there was no medium at all, no sea for light to swim in. The universe was emptier than anyone had dared to believe. Michelson, a careful man, repeated the test over and over, convinced he must have missed something. But each time, the result was the same. No difference, no drift, no ether. The light somehow simply was. It moved through space as if space itself were enough. When the news spread, it was met with disbelief. Generations of scientists had depended on the ether to make sense of motion, to fill the loneliness of the void. Without it, the entire framework of physics felt unstable. How could waves exist without a medium? How could light travel through nothing? The answers, it turned out, would not come until a young man in Switzerland, Albert Einstein, showed that light didn't need a medium at all, because its speed was a property of space and time themselves. But in the quiet moment of the experiment itself, before those ideas emerged, there must have been something oddly peaceful in that absence of result. Imagine the scene. A beam of light split in two, travelling across still air and polished mirrors, recombining in silence. No flutter, no flicker, no sign of resistance. Just perfect symmetry. What Michelson and Morley discovered wasn't a failure. It was the first touch of true nothing. For the first time, humanity had verified that space could be utterly still, not filled with any secret ocean or hidden substance, but defined by its own emptiness. The void was not chaos. It was consistent, calm, elegant. Light didn't need a sea to swim in because it was the sea. It carried its own rhythm, its own self-contained motion, through the openness between worlds. It's strange, isn't it? For centuries we had feared nothingness, and when we finally found it, it was beautiful. Not a void that devoured, but a stillness that allowed movement. The absence of ether didn't stop light, it freed it. And yet, the story of nothing was far from over. Once scientists learned to create vacuums and measure the speed of light, they began using that emptiness to build new things, to invent machines, to peer deeper into the atom, to discover that even inside the matter we thought was solid, there was far more emptiness than substance. It's as if each time we uncover what lies beneath the visible world, we find not more matter, but more space. From the sky, to the air, to the atom, reality keeps revealing itself as mostly empty, and yet, somehow, profoundly alive. The idea of ether faded quietly from textbooks, but it left behind a whisper that the universe, even when stripped bare, still carries structure and meaning. The silence of the Michelson-Morley experiment was not a dead silence. It was the hum of potential, the calm before an even greater discovery. As we drift forward, that discovery awaits. For soon, scientists will turn their eyes from the vast emptiness between planets to the smaller emptiness within atoms, and what they find there will be stranger still. A world where emptiness is not the absence of matter, but the stage upon which everything dances. The story of the vacuum, the silent, weightless space once feared as unnatural, did not end with philosophers or experiments about ether. It crept quietly into daily life, into laboratories and living rooms, into the machines that shaped the modern world. Once we learned how to make nothing, we began to use it. It started with glass. In the late 19th century, craftsmen learned to shape long, delicate bulbs that could hold a near-perfect vacuum inside. The first electric lamps depended on this emptiness. Inside each bulb, a thin metal filament glowed hot when electricity passed through it. Without air, the filament didn't burn, it shone. A pocket of nothing became a cradle for light. If you walk beneath the old street lamps of a European city, glowing softly amber through the fog, you're seeing nothing put to work. Each bulb is a tiny space without air, filled only with silence and radiance. We had learned to make darkness serve brightness. That same principle, removing air to protect and preserve, spread everywhere. In the early 20th century, engineers began building radio tubes, those glass cylinders with glowing filaments and wires that form the beating heart of radios, televisions, and the first computers. These vacuum tubes controlled the flow of electricity with astonishing precision. They hummed softly inside wooden cabinets, amplifying voices carried invisibly through the air. For the first time, human speech and music could leap across continents, carried not by messengers, but by waves of electromagnetic light, moving through the emptiness we had once feared. People gathered around their radios at night, listening to jazz or news from faraway places, never realizing that inside those glowing tubes, sound was being born from silence. In a way, we had turned the void into a tool, a collaborator. Nothingness was no longer an abstract idea. It powered our machines and lit our streets. We had, as one scientist joked, learned to make money out of nothing. But scientists, being what they are, could not stop at making devices. They wanted to know what that emptiness really was. They began using their new vacuum pumps to look deeper into matter itself. One of them, a physicist named Ernest Rutherford, set out to test an idea so simple it seemed almost foolish. What happens when you fire particles at atoms? He built an apparatus using a thin sheet of gold foil and a source of alpha particles, tiny, fast-moving fragments of atoms. His students, Geiger and Marston, aimed these invisible bullets at the foil and watched how they scattered. According to the accepted model of the time, atoms were thought to be solid, like little spheres of jelly with evenly spread charge. The particles they assumed would pass through easily or scatter only slightly. But that's not what happened. Most particles did go straight through, as expected, yet every so often one bounced back, deflected as if it had hit something small and incredibly dense. Rutherford was astonished. He later said it was like firing a bullet at a sheet of tissue paper and having it bounce back at you. From that single experiment came a revelation. Atoms are mostly empty. Nearly all of their mass sits in a tiny concentrated heart, the nucleus, surrounded by a vast region of space through which electrons move, like faint sparks orbiting a distant sun. If you could scale up an atom until the nucleus was the size of a marble, the nearest electron would circle several kilometers away. Everything solid around you, the table, the air, even your own body, is built from such structures. Matter, it turns out, is mostly space pretending to be solid. You can feel that truth in small ways. When you press your hand against a wall, it feels firm, yet what really happens is that the electric fields of your atoms are repelling the electric fields of the wall's atoms. Nothing actually touches. The firmness you feel is the resistance of emptiness, the tension in the fields between almost infinite voids. That realization transformed the way we understood the universe. The void was not confined to the spaces between planets or stars. It was inside everything. Every object, every person, every thought rests upon vast distances hidden within the structure of matter. The vacuum, it seemed, was not outside of us. It was within. And just as industry had learned to harness nothing to create light and sound, science began to use this new understanding to probe even deeper. Particle accelerators would one day smash atoms together, peeling back the layers of emptiness to see what hides beneath. The results would only deepen the mystery. Smaller and smaller particles, more forces, more patterns, and always in between the same quiet space. It's easy to forget how strange this is. The chair beneath you, the floor under your feet, the planet itself, all are made of atoms, and those atoms are almost entirely empty. If you could compress all the empty space out of the human body, it would shrink to a speck invisible to the naked eye, but its mass would remain the same. We are, in the most literal sense, organized emptiness, a symphony of space and energy arranged into form. Perhaps that's why the vacuum has always fascinated us. It's not simply an absence, it's a mirror of what we are, fragile shapes suspended in nothing, held together by invisible forces glowing briefly in time, and yet, even after discovering the hollow heart of matter, the question remained: is emptiness truly empty? If the atoms that make us are mostly void, what fills the space between their particles? Is it complete nothing? Or could there be something else, something unseen, humming beneath that stillness? The next generation of scientists would soon discover that the vacuum is not a silent void at all. It is restless, alive with invisible motion. Even when stripped of every atom, every photon, every trace of matter, space itself continues to flicker. From the hum of old radio tubes to the shimmer inside the atom, we are slowly learning that nothing isn't nothing at all. It's the quiet from which everything begins. By the early 20th century, scientists had peered deep into the atom and found a world both intricate and empty. The solid world had melted into a haze of probabilities. Electrons no longer behaved like neat little planets circling a miniature sun. They moved more like clouds, appearing and disappearing, spreading themselves into shimmering possibilities. The closer you looked, the less certain things became. It was here, in this strange twilight between what is and what might be, that a young German physicist named Werner Heisenberg began to think differently. He was not interested in what couldn't be seen, only in what could be measured. If science was to describe nature honestly, he reasoned, it must speak the language of observation, not speculation. But as Heisenberg tried to pin down the motions of electrons, something peculiar happened. The very act of measuring seemed to blur what he was trying to see. When he focused on an electron's position, where it was in space, its motion became uncertain. And when he measured its speed precisely, its location dissolved into ambiguity. The two pieces of knowledge refused to exist together in perfect clarity. At first, this felt like a technical limitation, a matter of instruments not being fine enough. But Heisenberg realized it was deeper than that. The fuzziness wasn't in the tools, it was in the nature of reality itself. The world, at its most fundamental level, would not hold still for inspection. He called this strange relationship the uncertainty principle, though it might be better understood as the principle of gentleness. You cannot observe something without touching it, and in touching it you change it. Nature protects its secrets not with walls, but with trembling. Imagine holding a camera and trying to photograph a hummingbird's wings in motion. The faster your shutter speed, the clearer the motion, but the less light you capture. If you slow the shutter, you gather more light, but the image blurs. No matter what you do, there's trade-off. Precision in one realm costs clarity in another. On the atomic scale, the same rule applies, but infinitely more so. The universe is not a static picture. It's a film in perpetual motion. To freeze it is to lose its movement. To see its motion is to surrender its stillness. Heisenberg's insight was revolutionary, yet deeply human. For centuries, science had sought certainty, a world of perfect predictability. But here, at the smallest scales, the universe whispered a different truth. Certainty is an illusion. Reality is not a machine turning with clockwork precision. It's a dance full of rhythm and uncertainty, graceful in its imperfection. This idea unsettled many. Even Einstein, who had redefined time and space, resisted it. God does not play dice, he famously said. But Heisenberg's universe didn't ask for belief. It simply was. The dice weren't in God's hands. They were woven into the fabric of existence. At this microscopic level, even the vacuum, the space we had once thought of as truly empty, began to behave strangely. According to the new quantum view, space and energy were linked, just as position and motion were. You could never pin both down exactly. The shorter the time you tried to measure, the more uncertain the energy became. It was as if emptiness itself had a heartbeat. Over tiny fleeting moments, space could borrow energy from nothingness, create a brief flicker of light or a pair of particles, and then return the energy before anyone could notice. It was a kind of cosmic accounting trick. Nothing ever violated balance, but everything flickered. You can think of it like the shimmer on the surface of a still pond. To the eye, the water looks calm, yet tiny ripples dance across it, invisible until they catch the light. Space, too, has these ripples, microscopic fluctuations that never quite vanish, even when everything else is gone. This trembling of the vacuum would one day explain much of what happens in the quantum world, how particles interact, how forces arise, even how galaxies might have formed from the smallest variations in that early cosmic mist. But for now, in Heisenberg's time, it was simply an implication, an almost poetic hint that nothing is truly still. In this picture, emptiness becomes a living field, always on the edge of becoming something. The vacuum, far from being lifeless, hums softly with potential, and the uncertainty principle is its rhythm, the steady pulse that says, everything fluctuates. It's tempting to think of this as chaos, but it isn't. It's more like music played so softly you can barely hear it. The notes blur into one another, forming a continuous hum. Within that hum lies every possible melody that could one day be played. When Heisenberg looked back on his discovery, he described it not as a defeat of knowledge, but as a reminder of humility. What we observe, he said, is not nature itself, but nature exposed to our method of questioning. In other words, reality is not a painting waiting to be admired. It's a conversation, one that answers differently depending on how gently you ask. And so the search for nothing had turned a corner. We had reached the edge of what could be called empty, only to find motion and possibility waiting there. The closer we came to stillness, the more movement we found. The more precisely we tried to describe the world, the more it slipped through our fingers like light through water. Perhaps this is what makes existence so beautiful. Its refusal to be pinned down. Everything trembles, from the smallest particles to the stars themselves. The same uncertainty that governs the flicker of electrons governs us too. The unpredictability of thought, of love, of life. In a sense, we're all quantum beings, living in the delicate balance between knowing and mystery. And if even nothing can flicker, then perhaps creation was never a single event, but an ongoing process, an endless trembling of the void, from which new things are always waiting to appear. As we drift onward, that idea will bloom into something astonishing, that the vacuum itself, this restless sea of almost nothing, may have given birth to everything. The galaxies, the stars, and even you. If you were to walk through the halls of Cambridge University a century ago, you might have passed a young man moving quietly among the echoing corridors, head slightly bowed, hands in his coat pockets, eyes unfocused as if tuned to a distant frequency. His name was Paul Dirac. Those who knew him said he rarely spoke unless spoken to. When he did, it was with such economy that friends joked about measuring conversation in Diracs, a unit of silence interrupted only by necessity. But inside that silence, whole worlds were unfolding. Dirac's mind was not noisy like most, it was crystalline, precise. Where others saw confusion, he saw symmetry. He once said that the only true guide in physics was beauty, that a theory should be so elegant that it felt inevitable, as though the universe itself had written it, and we were merely discovering its handwriting. He was born in Bristol in 1902, a shy boy with a love for mathematics that bordered on reverence. His father, a strict schoolteacher, insisted that every sentence Paul spoke in French. The result was that he spoke very little at all. That quietness became his language. He learned to think in numbers and patterns instead of words. Years later, after his rise to prominence, the actor Cary Grant, another Bristol native, met Dirac at a dinner party. They exchanged only a few words before Dirac retreated into thought. Someone later asked what they had talked about. "Nothing much," Grant said with a smile, "but I believe I understood him completely." Dirac's gift was to turn mathematics into poetry, language without ornament, yet luminous in its precision. In the 1920s, the world of physics was changing rapidly. Quantum theory had revealed a microscopic realm of uncertainty and probability. Einstein's relativity had redefined time and space, but the two great ideas did not fit neatly together. Quantum mechanics described the very small, relativity described the very fast. What happens, physicists wondered, when something is both small and fast, like an electron moving near the speed of light? Dirac sought to unite these worlds. For months, he worked alone in his room at St. John's College, surrounded by sheets of scribbled paper. He would sit motionless for hours, lost in quiet concentration. Then, one evening, his pencil found the line he'd been searching for, an equation so elegant that he described it as the most beautiful in physics. We don't need to see the symbols to feel its meaning. In a single sentence of mathematics, Dirac joined two languages, the gentle pulse of quantum mechanics and the steady beat of relativity. It was like discovering that two pieces of music played in different keys were actually part of the same symphony. His equation described how particles such as electrons move and spin, but hidden within it was something unexpected, a mirror image. When Dirac looked closely, he realized his equation had two kinds of solutions, one for positive energy and one for negative. To most physicists, that seemed absurd. Negative energy didn't make sense, just as a ball rolling uphill without force would make no sense. But Dirac trusted beauty more than convention. He believed the mathematics was trying to tell him something, and it was. Within that strange symmetry lay the prediction of a new kind of matter, antimatter. For every particle that exists, there must be a twin with opposite charge, perfectly mirrored, perfectly balanced. Whenever something appears in the universe, its reflection appears too. This was not an abstract idea. It was a new way of seeing reality. The universe, Dirac suggested, is built on duality. For every push, a pull, for every rise, a fall, for every particle of matter, a ghostly counterpart waiting just beyond our reach. If the two should ever meet, they would vanish together, leaving behind only pure light. Dirac had uncovered something profound, symmetry woven into the fabric of existence itself. To him, this wasn't a coincidence. It was a sign of harmony, a quiet perfection hidden beneath the chaos of daily life. When he published his theory, many dismissed it as mathematical fantasy. But 4 years later, in 1932, the American physicist Carl Anderson discovered a particle in cosmic rays with the same mass as the electron, but a positive charge. It was exactly what Dirac's equation had foretold. The positron, the electron's mirror twin, was real. Overnight, the strange symbols on Dirac's page became proof that the universe contains its own reflection. The void, it seemed, was not empty at all. It was balanced. For every spark of existence, there was a shadow spark, born equal and opposite. Dirac's discovery changed not only physics but philosophy. The idea that symmetry governs everything, that even nothing obeys balance, gave the universe an unexpected grace. Creation was not chaos but correspondence. Every action had its echo. Every note had its harmony. When asked about his discovery, Dirac simply said, "It is more important to have beauty in one's equations than to have them fit experiment." To him, beauty was not decoration. It was truth wearing its simplest form. Even today, when physicists look into the heart of reality, they see his symmetry everywhere. Matter and antimatter are not rivals but partners in a cosmic dance, appearing together and vanishing together. That balance is what keeps the universe whole. Dirac lived much of his life in quiet solitude, never comfortable with fame. He once said that in a world filled with noise, silence was the only honest state of mind. Perhaps he was right. Out of that silence, he heard something eternal, the hum of mathematics that shapes everything from atoms to galaxies. And in the same way, perhaps the universe itself speaks that language: symmetry, simplicity, and balance. Whenever something exists, its reflection stirs in the dark, bound by the same rules, the same grace. As we drift further into this story, we'll see what happens when those reflections meet, how matter and antimatter find each other and, in their union, disappear. For in the brief instant of their vanishing, they reveal a truth older than stars, that creation and destruction are not opposites, but two halves of the same breath. If Dirac's equation was a kind of cosmic poem, then its verses were written in light and reflection. His discovery that every particle of matter has an equal and opposite twin wasn't just a mathematical curiosity. It was an invitation to imagine the universe as a place where balance is not optional but essential. For every spark that flares into existence, another spark appears, identical in every way except that its charge flows backward. We call this mirror form antimatter. It is the twin of everything you see, a shadow that behaves exactly the same, except that it holds its energy in reverse. To describe it in equations would take pages, but you don't need them to feel the meaning. Think instead of two dancers facing each other across a mirror, every step one takes, the other matches in perfect opposition. If they ever meet, they don't collide violently. They simply dissolve into light, the energy of their motion turned pure. This is not fantasy. In laboratories around the world, we have watched this delicate exchange play out. When a particle of matter meets its antimatter counterpart, both vanish. Their mass doesn't disappear, it transforms, following the quiet rule that energy and matter are two faces of the same thing. The result is a burst of light, photons, racing away at the speed that defines the universe itself. It is one of nature's most graceful acts of symmetry. Where we might see destruction, the universe sees completion, a return to balance. The two twins bow, embrace, and become light. This might sound like something rare and remote, but in truth, it happens all the time. When you place your hand near a warm lamp, the light that touches your skin was born from such unions. Deep within the sun, matter and antimatter meet constantly as particles collide at unimaginable speeds, vanishing into the light that bathes the earth. The glow of every star is a kind of farewell, a billion tiny dances of vanishing twins. Yet this balance is never perfect. If the universe had produced matter and antimatter in exactly equal amounts, every particle would have found its twin long ago and all of creation would have dissolved back into light. There would be no galaxies, no planets, no you sitting here listening to this story. Something very small and still unexplained, tipped the scale ever so slightly in favour of matter. For every billion pairs that vanished together, one particle remained. That 1 in a billion survivor became the seed of everything that followed. Stars, oceans, memories, and breath. You might say the universe exists because of an imbalance so subtle it's almost poetic, a single skipped beat in the rhythm of symmetry. But before we reach that part of the story, let's linger for a moment on the dance itself, the constant flicker between being and not being. Even in the emptiest reaches of space, this ballet continues. Quantum physics tells us that the vacuum isn't a silent void, but a restless stage. Tiny pairs of particles and antiparticles are born from nothing, live for the briefest fraction of a second, and then disappear again. They are called virtual particles, though the word virtual doesn't mean imaginary. It means fleeting, temporary, too brief for our instruments to hold. Picture them as sparks on the surface of an invisible ocean, each rising and fading so quickly that the sea itself seems smooth. But those flickers are real. They give the vacuum its quiet shimmer, its hum of energy that never quite stops. If you could slow time enough to watch this hidden choreography, you would see the vacuum alive with motion. Pairs appearing, swirling, touching, and vanishing over and over. Each pair is born together, matter and antimatter, twins for a heartbeat, and each ends the same way in reunion and release. The universe, even when it seems still, is full of these tiny farewells. In a sense, Dirac's symmetry lives everywhere. The particles that make up your body exist because of that same rule, balance and return. Your heartbeat, your breath, the electric signals firing through your neurons, they all trace back to a universe that cannot stop pairing opposites. You're made of matter, but the shadow of your being is written in antimatter. Somewhere in the mathematics of the cosmos, your twin exists too, not as a mirror image of flesh, but as the idea that every presence implies its opposite. And if you ever feel the world pulling in two directions, light and dark, creation and destruction, it may comfort you to know that the universe itself lives that way. Its foundation is duality, not simplicity. It does not fear opposites. It thrives on them. In the laboratories of CERN, Scientists have even managed to capture small amounts of antimatter, tiny clouds of positrons and antiprotons held in magnetic traps. They glow faintly when touched by matter, releasing light in elegant bursts, reminders of how thin the line is between existence and energy. Those experiments are more than physics, they are reenactments of the universe's earlier seconds, when everything that now exists was flickering in and out of being, unsure which side of the mirror it would settle on. It's humbling to realise that the very idea of annihilation is, at its heart, not about loss, but transformation. When matter and antimatter meet, their end is radiant. Their disappearance fills the darkness with light. Perhaps that is the deeper truth. Even destruction, at the smallest scale, is a form of giving. Dirac, who discovered the symmetry, once said that the equations themselves seemed alive, that mathematics was not invented but found. Maybe that's why his quiet logic resonates so deeply. It tells us that creation doesn't happen instead of nothingness. It happens through it. The void does not oppose existence, it gives it structure. So now, as we follow these tiny twins through their endless waltz of appearance and disappearance, we can feel the universe breathing again, just as it did when it first began to expand. Each flicker is a note in a vast, silent song, one that fills every atom and every corner of space. And beneath it all, there is that same soft hum, the sound of balance maintained through endless change, the music of nothing keeping time. Our path now carries us toward the next quiet revelation, the moment when scientists finally listened closely enough to hear that hum, to measure the faint vibrations of the vacuum itself, and to realize that the silence of space is not silent at all. If you could float in the deepest silence between stars, with no air, no dust, no light, nothing at all, you might imagine the world would finally fall quiet. After all, isn't that what emptiness means? Stillness, perfection, the end of all motion. But in the mid-20th century, a few scientists began to suspect that even the calmest vacuum might not be entirely at rest. They wondered, what if nothing itself was alive with movement? One of them was an American physicist named Willis Lamb. His story begins in 1947, in a laboratory filled with humming equipment and the soft glow of cathode tubes. On his desk stood a machine designed to test one of the simplest atoms in the universe, hydrogen. By that time, the structure of hydrogen was supposed to be fully understood. Its single electron orbited its single proton in predictable ways, and every energy level had been mapped with exquisite precision. But when Lamb began to measure it, he noticed something strange. The electron didn't sit exactly where the equation said it should. Its energy was slightly, barely off, like a violin note just a fraction out of tune. At first, this might sound trivial, but the precision of Lamb's instruments made the difference undeniable. Something was pushing the electron ever so gently, as if the emptiness surrounding it were not perfectly smooth but faintly rippled. To explain it, he and his colleague Robert Rutherford ran the experiment again and again. Each time the same result, a tiny, consistent wobble. The hydrogen atom wasn't following the neat lines that theory had drawn. There was a kind of turbulence in the void. Imagine an airplane flying through a clear sky. The air seems perfectly calm, yet the plane shudders slightly as invisible currents brush its wings. The space around an electron behaves much the same way. Even in perfect vacuum, there are invisible eddies, tiny fluctuations of energy rising and falling too fast for us to see. The electron moves through that sea, and the waves nudge it, shifting its tune ever so slightly. This phenomenon became known as the Lamb shift, though the name hardly captures its quiet mystery. What Lamb had discovered was not a flaw in the atom, but a window into the true nature of emptiness. The vacuum, he revealed, is not empty at all. It seethes with energy, a constant hum of virtual particles flickering in and out of existence, They appear, vanish, and reappear, borrowing energy from nothing, repaying it almost instantly, creating a gentle background buzz that fills the cosmos. To the human ear, it would be silence, but to the electron, it is a landscape alive with motion. The vacuum is like an ocean whose surface looks calm from afar, yet beneath it, waves never stop forming and dissolving. When the results were announced, physicists were astonished. The equations of quantum theory, when interpreted through the lens of these fluctuations, matched the measurements exactly. The harmony was uncanny, as if nature herself had whispered yes to their suspicions. This invisible vibration, this quiet hum of the vacuum, turned out to be one of the most profound discoveries in modern physics. It meant that the energy of the universe could never reach zero. Even if every atom, every star, every photon were removed, space would still pulse faintly with possibility. The nothing between things was, in truth, everything waiting to happen. And that realization changed how scientists viewed the cosmos. If the vacuum is alive with energy, then it might have shaped the universe itself. Those tiny fluctuations, the same ones that made Lamb's hydrogen atom waver, could have been the seeds that grew into galaxies. Small ripples in the sea of nothing could have become the waves that formed stars and planets, simply because emptiness refused to stay still. The thought is dizzying. Every cluster of galaxies, every sunrise, every quiet heartbeat might trace its ancestry to the restless hum of the vacuum, to that faint shimmering whisper that Lamb and Rutherford first heard through their instruments. When you think of it that way, emptiness stops feeling empty. It becomes the ultimate instrument, the first stage on which the music of creation was played, and perhaps that's why the universe seems to hum with a kind of rhythm even in its vastness. Everything, atoms, stars, consciousness itself, moves to the same underlying beat. Of course, Lamb himself was a practical man. He didn't speak in poetry. When asked about his discovery, he described it simply as a correction, but others saw in it a glimpse of something deeper, a universe where stillness is an illusion and even the void has breath. If you were to close your eyes right now and listen, not with your ears, but with your imagination, you might hear it too. Not an actual sound, but the sense of quiet movement everywhere, the slow turn of the earth, the drift of galaxies, the whisper of the vacuum's own vibration. It is not noise. It is existence itself, humming softly to no one in particular. In the centuries since Lamb's experiment, scientists have measured this hum in many forms. In the faint warmth of the cosmic microwave background, in the delicate flicker of quantum fields, in the subtle push of invisible forces. Each time the pattern holds, the vacuum is never silent. And so, the story of nothing comes full circle. What began as the fear of emptiness has become the discovery of fullness. The void is not a hole in reality, it is its foundation. Without that restless trembling, there would be no motion, no matter, no light. Nothing would truly be nothing, and the universe would be too still to exist. It's a comforting thought in a way, that even in the quietest darkness, something is always moving, softly, unseen, keeping the cosmos alive. As our journey continues, we'll follow that hum outward again to the edges of time itself, where those same quantum ripples once shaped the newborn universe. There, in the faint glow of creation's first light, the fingerprints of nothing still remain. Imagine looking at a photograph of a newborn baby and realizing that, in some mysterious way, the patterns on that tiny face had been written before birth, etched in the unseen motions that happened long before time had a name. That's what scientists felt when they first mapped the faint afterglow of the Big Bang, the cosmic microwave background. It was a portrait of the universe as an infant, only 380,000 years old, and it revealed something astonishing: the fingerprints of nothing itself. The story begins billions of years before that photograph was taken, when the universe was smaller than an atom, still wrapped in its earliest darkness. In that era, everything was compressed into a dense, swirling soup of energy. Space wasn't a calm expanse yet. It was turbulent and hot, vibrating with the same quantum fluctuations that Heisenberg, Dirac and Lamb had hinted at. The vacuum, restless as always, flickered with temporary particles, tiny sparks of being that rose and fell faster than any clock could tick. Those infinitesimal tremors, the same hum Lamb detected around his hydrogen atom, were present everywhere, rippling through the universe's first moments. At that unimaginable scale, nothing could ever be still. And that restless, unpredictable motion would become the seeds of everything that exists. To picture it, imagine a calm pond disturbed by a passing breeze. Ripples appear across its surface, tiny and irregular. Now imagine that pond expanding, growing larger and larger in every direction, faster than thought itself. Those ripples stretch with it, frozen in place as the water spreads outward. That's what happened to the universe in its infancy. Quantum fluctuations, once microscopic, were magnified as space ballooned in the event we now call cosmic inflation. In that brief, breathtaking instant, the universe grew from smaller than an atom to larger than a galaxy cluster. And embedded within its expanding fabric were the faint imprints of those original tremors. They would become, in time, the architecture of everything, the places where matter gathered to form galaxies, stars and worlds. Billions of years later, when the light of the cosmic microwave background was finally captured by satellites like WMAP and Planck, those ancient ripples appeared as tiny differences in temperature, variations as small as 1 part in 100,000. Yet those minute irregularities were the fingerprints of creation, the frozen echoes of quantum nothingness. The warm spots would become clusters of galaxies. The cool spots would become cosmic voids. It's humbling to think that all of cosmic structure, the vast web of galaxies stretching for billions of light years, traces its origin to fluctuations smaller than a single atom. The universe we see was sculpted not by violence, but by trembling. You can see these fingerprints today in the images scientists call baby pictures of the universe. They show a mottled sphere of soft colours, reds, blues, yellows, each representing a tiny change in temperature. To most people, it looks abstract, like an ancient mosaic or the pattern on an eggshell, but to physicists, it's the evidence that nothingness itself once stirred. Every colour is a memory of the vacuum's gentle noise. If you run your fingertips across a piece of wood, you can feel faint lines and grooves, the grain that tells how the tree once grew. The cosmic background is like that. The universe may seem smooth and uniform from afar, but beneath its surface lies a pattern of tiny imperfections, each one a relic of the quantum waves that once rolled through nothing. Without those imperfections, nothing would have condensed. No stars would have formed. The sky would be blank. We owe everything that exists to the fact that nothing could not hold still. This connection, from Heisenberg's trembling uncertainty, to Dirac's symmetry of existence, to Lamb's vibrating vacuum, finds its grand expression here. What began as mathematical whispers in small laboratories now speaks in the voice of the cosmos itself. The same principle that nudges an electron slightly off its course gave shape to galaxies, to the spiral arms of the Milky Way, to the sunlight warming your face right now. There's something almost poetic in that symmetry of scale. The tiniest fluctuations and the grandest structures share a common heartbeat. From the quantum to the cosmic, the rhythm is the same, a hum that refuses silence. When we look at the night sky, every star, every luminous thread in the darkness is an echo of those first irregularities. The galaxies are the ripples of nothing made visible. The void between them is not absence, but continuation. The places where the early tremors leaned away from creation, leaving space for quiet. Sometimes scientists describe this process with words like inflationary perturbations and quantum field variations. But beneath the jargon lies something deeply human. The story of the universe is also the story of balance, between stillness and motion, emptiness and form, order and chaos. Even now, the same dynamic continues. Space itself expands, and the quantum fields that fill it never truly rest. The hum lamb once measured still vibrates everywhere, just more softly now, stretched thin by billions of years of cosmic growth. If you could somehow hear it, it would sound like the faintest sigh, a memory of creation's first breath, echoing through eternity. In that sense, we're all listening to it, all the time. It's in the radiation that drifts through your body each second, in the whisper of cosmic rays, in the warmth that lingers in empty rooms. The universe has never stopped singing its quiet song. We simply grew used to the melody. And yet, when you think of it deeply, it's almost overwhelming. Every movement, every heartbeat, every thought is a continuation of that first fluctuation. The trembling of nothing that became everything. The stars are not separate from the void. They are its self-portrait, light drawn from silence. As our quiet journey nears its end, we begin to see the whole arc of the story. What we once called nothing turns out to be the womb of creation, the source of all symmetry, all motion, all possibility. The void, restless and radiant, shaped the galaxies and in doing so shaped us. Our exploration now moves toward its final breath, to the stillness between stars where everything that has ever existed will one day dissolve back into quiet. And there, in that silence, we might finally understand nothingness and existence were never opposites. They were always partners in the same cosmic dance. If you look up at the night sky on a clear evening, what you're really seeing is memory. Ancient light crossing a dark ocean of time. Every star, every faint glimmer in that endless expanse is a message from the past. Some of those messages began their journey before the Earth was born, before even the atoms in your body existed. And between those messages lies the truest mystery of all, the silence that carries them. We often think of the universe as something full, galaxies, planets, moons, dust. But most of it is empty. The distances between stars are so immense that light, travelling faster than anything else, can take centuries to cross from one to another. Between galaxies, that emptiness stretches further still. Vast, invisible plains of near-perfect vacuum, where a single particle might drift for years before meeting another. Yet this emptiness isn't dead. It hums softly with leftover energy, with the faint breath of creation that never quite faded. It is the quiet between stars, the pause between heartbeats, the space where being and nothingness touch. And though we call it void, it's more like a gentle presence, a kind of peace that holds the universe together. At the beginning of time, matter and antimatter were created almost equally. For every billion pairs that met and vanished into the light, one lonely particle survived. Just one in a billion. That's all it took for everything we know to exist. That slight imbalance is why the stars shine, why the oceans move, why your heart beats. We are the remnants of that ancient asymmetry, the lucky survivors of an otherwise perfect annihilation. It's humbling to think that the universe as we know it began not because of perfection, but because of a tiny imperfection, a skipped beat in the rhythm of symmetry. If every equation had balanced exactly, there would have been no galaxies, no Earth, no life. The stars would have flared once and gone dark, leaving only an ocean of light and silence. Instead, a small imbalance tilted the scales, and from that faint unevenness came everything. So in a sense, we're all made of mistakes, the universe's beautiful miscalculation. Out of near-perfect symmetry came asymmetry, And out of that came complexity, chemistry, and consciousness. The quiet between stars is the same quiet within us. The space between one heartbeat and the next, the pause between thoughts, the stillness that gives shape to motion. Even now, billions of years after that first flicker, the universe continues to expand, carrying galaxies farther and farther apart. The light from distant stars grows redder, stretched by space itself until it fades beyond visibility. One day, so far in the future that it defies imagination, even the nearest galaxies will slip beyond reach. The night sky will grow darker, and the stars we once saw as eternal will vanish one by one. But this isn't a tragedy. It's part of the same gentle rhythm that began long ago. The universe breathes, it expands, cools and rests. The stars that burn now will one day return their matter to the dark, becoming dust and quiet again. And from that quiet, perhaps new stars will one day form. It's easy to forget that we live inside that cycle. The atoms in your body, carbon, oxygen, iron, were forged in ancient stars. Long before you breathed, those atoms burned in the hearts of suns that lived and died billions of years ago. When those stars exploded, they scattered their contents into the cosmos, and over eons that stardust found its way here, to oceans, to forests, to you. You are, quite literally, the echo of vanished stars shining again for a brief moment in a different form. That's why the quiet between stars isn't loneliness, it's connection, space wide enough for transformation. Every silence holds the memory of sound. Every void holds the potential for creation. Even the vacuum, that restless hum beneath existence, keeps shaping reality in ways we're still learning to see. Scientists once wondered if the universe might end in fire, a final collapse back into the heat of its beginning. But now it seems more likely to end in calm, galaxies drifting too far apart to see one another, stars burning out, black holes fading into nothing. Not an explosion, but a sigh. The same breath that began everything will one day settle into stillness again. And maybe that's not something to mourn. Maybe that's simply how the universe rests. The same way we close our eyes at the end of the day, the cosmos too will one day fall asleep. Its light will fade, its sounds will hush, and in that vast dark quiet, every story it ever told will still exist, unwritten but never lost. When that time comes, if consciousness still lingers somewhere, it might remember what it felt like to be alive, to spin for a moment in the space between everything and nothing. And maybe it will understand that silence was never the opposite of creation, but its continuation. Because nothingness and infinity are not enemies, they are twins. One expands without end, the other receives without complaint. Emptiness is not absence, it is readiness. It is the pause that allows each note of existence to be heard. Without it, there would be no rhythm, no stars, no you. So when you step outside tonight and look up, try not to see only the light. Notice the darkness between. That darkness is not blank. It's the womb of everything, the quiet that made it all possible, the same quiet that hums within you when your thoughts grow still. The universe began as a breath and will one day return to quiet, but in between those two silences, it sings. And you, this small spark of matter, this pattern of stardust shaped by chance and time, you are part of that song. You are the moment the universe became aware of itself. So rest now, little fragment of the cosmos. The stars are still burning, the galaxies still drifting, the vacuum still humming softly beneath it all. You are exactly where you belong, between everything and nothing, between the inhale and the exhale of existence. And in that fragile space there is peace.